Hi, everybody. My name is Jason Hallows. I'm a director of a company called EcoSource Insight. EcoSource Insight has been involved in the water-related IT sector for the last 20 years. I'm going to be talking with you on the Smart Water Technology course that you're currently on with Empire Training. And specifically, I'm going to be discussing managing water-related risk and developing practical and implementable solutions. All right, so to start, we're going to start with this new buzzword called smart. So welcome to the world of smart. So we've got new smart meters, we've got smart communications, we've got smart houses, smart cars, we're heading to smart cities, and hopefully we'll have a smart world. Now, in many respects, I think these elements at the moment are overbuilt. Many of these applications are not as smart as we'd like to think they are. Going on to the Internet of Things, a really promising technology that's happening, that's connecting us with our devices into our electronic things and interconnecting those things together. The aspect is we're becoming more connected to things, but we seem to forget that technology is meant to connect people. And are we getting more connected associated with that? The technologies that we implement are supposed to help us as people and communities. Another element that is quite often being sort of touted as the new biggest thing is artificial intelligence. So the question is what could possibly go wrong? What you're having a look at over here is a Tesla on autopilot or auto drive. And what you see over here is it flying straight into the back of a lorry on its side. There are a number of reasons that this happened. And there's a number of reasons that autopilot or fully automated driving is not in place yet. If you're going to rely on AI technology, you need to be very aware of the downfalls that it could have or the pitfalls associated with it. Two excellent TED Talk videos which outline this. The Real Reason to be Afraid of Artificial Intelligence by Peter Haas, and another, which is The Danger of AI is Weirder Than You Think by Janelle Shane. I'd recommend that you go and view those. But essentially what happens with a lot of the artificial intelligence is, one, the training information that is used to train the systems is not comprehensive enough or not well selected. And the second aspect associated with it is that artificial intelligence is always trained and based on historical aspects, and it does not do very well in situations where history is not going to repeat itself. So if you've got a novel situation, don't expect artificial intelligence to perform well. And when these failures do occur, they can be pretty catastrophic. The next aspect that I would like to touch on is risk. From a risk perspective, and from a global perspective, we have definitely become more connected. We are more interconnected as a society. This means that the impacts associated with an event can have far, far-reaching consequences. They can have regional or even global impacts. Therefore, the consequences associated with specific events or hazards is increased exponentially compared to what it used to be. Added to this interconnectivity is the realization now that we are in a nexus. We're in a water and energy nexus. To move water, you need energy, and to generate energy, you need water. At the same time, you need water to grow food and to protect the environment. So water is an interconnecting element associated with many things, and therefore the risks associated with water have far-reaching consequences as well. There's perceived versus real risks. To a large extent, if we have a look at the financial aspects related to most businesses, water is actually a really small input cost. Yet the consequences of not having water or having too much water are extreme. And this is where the situation associated with perceived versus real risks becomes very, very clear. Now, one of the aspects that we must understand is that as we are moving with all this new technology, with the Internet of Things, etc., we're getting more and more information. But information is not knowledge. In fact, in many cases, too much information is a problem. We can become overwhelmed, and in actual fact, it can hamper decision making. So we need to have a situation where we get information in such a way that it enables our decision making and doesn't hamper it. If we have a look at the VAL system and just have a look at some of the risks associated with the VAL, a large amount of the water that comes into the VAL is supplied by 4 major transfer links, the main one being the Lesotho Highlands water project, followed by the Tugela VAL link. One of the issues associated with it is this is to secure the water supply to the VAL Dam, which obviously feeds the Rand water, which feeds Gauteng with water. So the economic heartland of South Africa gets fed via this scheme. There are concerns associated with it. There's a lot of uncontrolled irrigation on the streams that are leading into the VAL, which obviously deprive the urban areas of water. And that is one major concern associated with the VAL water use, and is obviously creating more and more risk associated with the VAL water supply. Added to the water quantity issues that are experienced in the VAL at the moment, we also see a large amount of non-compliance in terms of wastewater treatment works, which is increasing the amount of nutrient and E. coli inflow into the VAL. Consequence of this is increasing the amount and cost of water treatment in the VAL system, and obviously posing a risk of contaminated water supply into the Gauteng region. Consequence of this now is that with more or poorer water quality, water treatment costs in various municipal areas are increasing, and in some cases industrial water users are having to put in additional purification to what they used to in the past. So the risk associated with the water supply in South Africa is increasing. Here's a satellite photograph of VAL Dam, and what you see is all of those green areas are a consequence of algae and eutrophication in this area. Blue-green algae is notoriously difficult to treat from a water quality perspective and increases the water treatment costs enormously. Also, from a recreational perspective, you do not want to be using it in this VAL system when you've got high E. coli and high eutrophication. One of the critical aspects that's leading us to need to improve our water management is the notion of decoupling. Essentially, this notion is that the economic output occurring from industries, and in fact even from a countrywide perspective, needs to be decoupled from the resource consumption. In order to do this, we need to become more efficient water users, and this is pushing us towards more and more smarter solutions. At the same time, this also increases the economic impacts associated with lack of water and these types of things. If we have a look at the Carbon Disclosure Project, and we have a look at the reporting associated with water-related impacts, in the 2016 drought, 610 million rands was lost from just 10 companies. This is quite serious, obviously, from an economic impact perspective. The costs associated with the drought in Cape Town are much higher than this, except we haven't got those figures back yet. But one can see that the impacts on the financial impacts associated with poor water management and lack of water can be catastrophic or extremely high. If we have a look at the current situation, just to give you some perspective, in that 2016 year, the VAL system was around about the same level as it is at the moment. But the Lesotho system was actually much higher than it is at the moment. And remembering that the Lesotho is the main water supply backup to the VAL system, if we have another 2016 scenario this year, we could be in some serious trouble. So we are needing to become more and more efficient and effective at using our water resources, which are increasingly limited. So now we could ask some questions associated with smart technology. So what technology trends are important and that are enabling the improved management of water-related risks. How can these technology trends be accessed and used? How can these effectively be applied? What are the limitations currently which will limit the application of these technologies? And how should we take things forward? So to answer this question, it's important to realize that there's no single technology enabling trend that is going to improve water risk management. It is rather a combination of the application of these technologies that will increase improvements in terms of water resources management. And we've already seen some of these coming through. So in my view, probably the most important element is cloud computing. The second is improved computer processing. Then the improved sensors and information communication technology, or the Internet of Things, is extremely important. New satellite and remote sensing applications are increasingly becoming more important in water resources management. Artificial intelligence has a role to play. And then I think the critical aspect associated with this is that this information needs to be integrated into processing platforms that enable decision makers to make effective decisions without overwhelming them with the amount of information that is coming in these days. So let's have a look at cloud processing and cloud computing and the computing improvements associated with that. And I'm going to take you through a large number of examples of how computer processing and cloud processing has improved the situation. So if we have a look at this example, this is satellite data capture. This is a system that automatically captures the occurrence of water, so the surface area of water across the country, and in fact it can do it across the globe. Now, just over 2 years ago, the processing of this information from satellite capture to final product would have taken around about 8 weeks. So it was not a viable system to automate. With cloud processing now, this takes less than 6 hours, and it has actually been put into a specific product that is used to calculate the surface area of water across the country, and it is now being converted into volume data, and this will be released very soon. Other knowledge solutions that we can have a look at are a direct result of improved computer simulation ability, and this is particularly important in the modeling domain. Where previously we used to use simplified conceptual models, we are now able to use physical process-based models. This is a suite of models which we often use to do simulations that cover source to sea, range by DHI, which is probably the most comprehensive and interconnected range available globally. Here we see a system which is running groundwater. And the types of answers that we're able to get from that is dewatering modules related to mining, so dewatering planning or mine dewatering planning. Having a look at things like pore water pressure on the stopes and embankments in pits, tailings, seepages, overall mine water balances, and things like mine closure planning. So if we're able to look at these, this is highly complex 3D modeling with various systems that are running, extremely heterogeneous geology that is run through these systems, and they're able to create assessments which assist in the planning processes very effectively. With the new enabling environments, we're starting to see some of this information starting to move into the real-time domain. Here's a South African example, just having a look at groundwater recharge in specific areas. So what we're having a look at over here is the grey areas are reclaimed pits that have been filled in. And essentially what we're getting over here is that the recharge in those particular areas is very high, and those are the red areas, and then those are reflecting into the river system at a later stage. This enables us to analyze various things, such as the directions and flows of water in particular areas, and it gives us an idea of how we can better manage these systems. There's a large amount of data which is now easily processed, which can be used to parameterize these models very effectively. And it allows us to get an idea of the full dynamics associated with these systems instead of simplifying them. The types of information that this can produce are things like seepage analyses and ideas of exactly where water is going in specific regions. Here we have a situation where we can have a look at particle tracking. This gives us an idea of where water is flowing from a tailings pond in this particular case and how long it's taking to get there. And this information combined with water quality assessments can very effectively be used in decision making. You can get an idea of the speed of these flows. The other aspect associated with cloud-based computing or various computing setups is that we can now run through a larger number of scenarios than we ever did before and analyze systems in a lot more detail. This is just a water availability assessment up in the Zambia region. Having a look at flood flows, the newer technology with two-dimensional and three-dimensional simulations allows us to have a look at much more effectively, and the equations associated with those can be more complex. Here we're looking at a Newtonian versus a non-Newtonian mud flow. Water moves down far quicker than the mud flows do. Just to give you an example of a system that we would not have even been able to model 10 years ago, and this is the Lower Mkomati floodplain. And what's quite nice about this is it's a two-dimensional flooding example. And the advantage of the two-dimensional flooding is that we're able to get the velocity as well as water depth in specific areas, as well as duration. And obviously the damage causing or hazard potential is a consequence of all three of those particular parameters. So having a look at this is a huge simulation, more than 1 billion grid cells altogether. 15 different scenarios were run. The time increments between, or the time step was less than a few minutes. Simulation period was roughly about 14 days. And the full simulation took less than a month to run for all 15 of those scenarios on a large cloud-based supercomputer. This could not have been done even 10 years ago, as I've mentioned. Here is an example of some flood. This is actually in Hekras. This gives you an idea of how simulations can be run, two-dimensional flood simulations. This was not possible previously. And what you can see over here is we've got water depth, and we'll zoom in shortly. And now that we've zoomed in, you can see the velocity vectors associated with the flow in these different areas. And the hazard causing potential is related to both the depth, velocity, and duration of flow, which we can then simulate into hazard potential. This is another area where computing advancements have allowed us to simulate things that we wouldn't have previously been able to do. This is actually a 3D simulation, but shown in 2D, of wastewater intrusion into the Danish harbour. They have coupled drainage systems. What we can see over here is where that water flows. This allows for effective planning, and these systems are now being integrated into real-time systems so that you can warn people not to go and swim in those specific areas. This is a local example at the Knysna Heads, looking at jellyfish intrusion into the Knysna Lagoon. This was an example simulation that we're hoping would be used to look at the endangered endemic populations of the Knysna seahorse in this particular. New sensor technology, the large number of different sensors that are being developed from electronic water meters right the way through to various water quality sensing devices and things like automated monitoring of dam walls with automated theodolites and these types of systems set up. So there's a lot more information that can be generated from water sensors, not just in terms of flow, but also in terms of water quality. There's also other technology which is making it easier to monitor a larger number of elements very quickly. This is a water quality analysis done with the bag method. It's around about 98% accurate. Allows for reasonably quick analysis, a few minutes to run this analysis. And basically this information is then taken with a cell phone setup, which tells us exactly whether the E. coli counts are too high in these particular water samples. And that information can be collected and sent by cell phone very effectively and quickly. Traditionally, this type of analysis would have taken a couple of weeks. So that's a massive improvement in terms of this. This information is becoming available on a near real-time or real-time basis. Remote sensing technologies. As shown before, we can automatically pick up water surface areas across different regions. Obviously, this gives us an idea of the water availability or water extent in those particular regions, which can be important for anything from transport in particular regions to actual water supply. We can also look at things like currents of water and statistics related to that, which gives us information on which areas are perennial versus ephemeral sort of wetlands, and much other information in these areas. We believe that this setups can be used to have a look at bathymetry changes and sedimentation in larger reservoirs, something that we're working on at the moment. Safety concerns can be analyzed. This is a tailings facility where we've done a flood simulation on that. And what we can do is we can actually monitor these tailings facilities from satellite. And if conditions are breached, we can send out warnings related to that. Water quality is now also being able to be picked up from satellite, and this information can be very valuable in terms of scheduling water treatments and actually analyzing and understanding health risks from a recreation and treatment perspective. Yeah, we can see some other satellite products. This is one related to the removal of tailings from specific facilities and pit changes. This gives us an idea of mine yield, can also give us an idea of the safety in tailing facilities in mine areas. Just having a look at the Internet of Things, probably the most critical aspect is that there's a lot more smart devices. So a cell phone can become an information collecting device, and many other devices as well. So more devices are reporting more information, and the communication technology is improving, and more importantly, it's getting cheaper and cheaper. So now it's much easier for us to set up telemetry systems which can report information to us much more effectively. And technologies such as Starlink are enabling remote locations to now become accessible. Artificial intelligence might have been slightly disparaging about artificial intelligence earlier, but it certainly has its place to play in water systems. But we need to be aware of its limitations. So you should apply it when you have a lot of data available and can effectively train the AI systems. It is quite effective when the outcomes are directly attributed to inputs and changes that are not too far removed in space and time. So it can be applied quite effectively in urban water systems, groundwater systems, and your river systems. It's not necessarily as effectively applied, generally because the impacts are quite heavily removed in time and space. And again, physically based modeling systems are probably more effective to get some of the information associated with that. An application of both artificial intelligence and the physically based systems could be very effective. It's also effective when historical conditions are very likely to replicate themselves. As mentioned earlier, when you get out of the parameters that the systems have been trained on, you can get very poor results and can result in catastrophic failures, as was emphasized by that car video that you saw earlier. Optimized decision making is quite important, and this seems to be an effective application of these systems, which I'll give you an example of very shortly. So, as I mentioned, smart water estates or water smart estates and these types of things in urban scenarios, AIs can be very effective with this. They can pick up changes in trends and patterns very effectively, can detect bursts, leaks, and problems in urban systems quite effectively. They've been applied for this in a number of regions. Other aspects related to this is the Venice barrage. And what you've got over here is a climate and tide simulation model running. The gates on the barrage are lowered or heightened according to the information that's provided here. And in actual fact, an AI came up with a better optimized solution than a number of PhD people had managed to do over a 10-year period. So in this particular case, the application of both physically based modeling and artificial intelligence came up with an improved solution in a much quicker time. So bringing it all together, the key aspect that we've got is we've got a lot of data, and that data might be coming from many different sensors. And to a degree, if this information is not effectively combined, it can be very much like the system that you've seen in Zambia over here, where these records are just paper-based records, very poorly managed. And if you want to capture that, you need to make that data useful. So you have to capture that information into systems that can summarize it and create a situation that is useful. Incidentally, the person who showed us this was very proud of their database. As you can imagine, that took a long time to get it into electronic format, which was more usable and more user-friendly. So if we have a look at information management and decision support systems, where is an area that we do a lot of work in. How can our solutions help you? Well, we have systems that allow for management of data and large amounts of data. That it can analyze and process that data and generate information from that data quite quickly in terms of reports associated with different statistical analyses. They can actually collate and summarize information very effectively. So the information management is quite critical. Then we have the planning components, and the planning components includes the modeling systems. This is where you're able to run scenarios and see what the impacts associated with different decisions might be. So the planning components usually involve the integration of some sort of modeling setups on top of the data management. Finally, we have the operational components, and this operational components allow for the initiation and running of specific actions. So that can be scheduled actions such as the collection of data or the importing of data from different sensors, as well as the response to specific events. So let's say there's a transgression associated with a high flow. It might initiate a flood model to be set up, as well as sending out warning information in terms of alerts and alarms to different people in different areas. Okay, so these are integrated systems, and to give you an example of some of this, these integrated systems, this is actually the Orange Fish Sunday system. Again, information coming in from a number of water flow sensors as well as water quality sensors, and that information is used to schedule releases from Gariep Dam through 80 kilometers of tunnel to an outlet at a place called Tebus. That water then flows down the system and eventually actually ends up in the Nelson Mandela metropole. So the effective management of these releases can save quite a lot of water and improve water quality on the system. What you see over here is the contribution to improved efficiencies where the system was running. It was around about a 50 million meter cube per annum reduction in the flows through the tunnel. That's around about 1/14 of the amount of water that is released through the Lesotho Highland scheme on an annual basis. And it's also
roughly around about 1/14 of the, or 1/12 to 1/14 of the water that's released through the Orange Fish Funnel. This water can be used for hydropower production from Gereep Dam, which has a direct financial contribution, as well as improving the water um, security of the downstream farmers, which also has obviously an economic implication related to that. Other integrated systems, we're running some stuff for Gani Water at the moment, which improves their bulk water supply. And we're now currently setting up a whole lot of urban water systems with them to improve their distribution systems. Flood forecasting is obviously quite important, and an effective flood forecast can allow people to effectively um, anticipate a flood flow coming down and take appropriate mitigation actions associated with that. That can save millions of rands to affected communities and obviously save lives related to that. So things like removal of pumps from irrigation areas is quite critical, as the flooded pumps can be broken or damaged, and other aspects related to putting up flood protection and embankments in specific areas can protect certain critical infrastructure. The Inkamati Sutu Catchment Management Agency has been using a lot of these applications of integrated systems where information comes from different sensors and provides information on how they should schedule releases of water on the system. And in actual fact, there was a paper written by the IUCMA which showed that under drought conditions, they were still able to um, supply their communities with water without implementing excessive restrictions that have happened in some of the other areas in the country. These are just examples of the dashboards used to run that system and provide managers with that information. So in conclusion, as stated before, no single smart system is going to be the holy grail in resolving a lot of the water management issues that we face today. But a use of a collection of these systems together could very well improve water management and help produce a more sustainable South Africa going forward. I hope you've enjoyed this talk, and thank you very much for listening. Bye-bye. If you've got any queries, please don't hesitate to contact me.